things. It's been interesting for me listening and looking at some of the titles of the talks that are taking place. For about 4 or 5 years ago, I did another keynote at Cloud Asia, right at the beginning of the Cloud Asia series, about the time when we moved away from Grid Asia. And at that particular point in time, most of the cloud talks were things like, what is the cloud, how do you build the cloud, all those type of things. So now it's interesting to see 4 or 5 years, 3 or 4 or 5 years on, that cloud is just so pervasive now. We're not really talking about what is cloud, but how is cloud changing people's lives. So some of the things I want to talk about here is how is cloud and things like mobility and big data changing the way we do things in business. Because I come from the business side, I'm not from the research side, although I run a research lab. I run a research lab at HP, which is fundamentally a big enterprise business. So my company is 75 years old. HP started a long time ago in Silicon Valley, birthplace of Silicon Valley. We started in a garage by 2 guys, Bill and Dave, and we started with $500 worth of funding capital. That was it. It was probably quite a lot in those days. First product was an oscillator which Walt Disney used in the film Fantasia. But if you roll forward 75 years, we've changed quite significantly as a company. We're in lots of different segments: financial services, software, enterprise services, printing, and PC. I see we've got a Dell here, but it's okay. I'll still press the buttons. And we're $100 billion in company. So we went from $500 to $100 billion, one product to gazillion products. We operate in 170 companies. We have 300,000 employees. So what did we decide to do? You probably read the news recently. For our 75th birthday present, we decided to split the company in half, which is a journey we're embarking on now, which is going to be quite interesting for us as we look at various things like cloud, mobility, and big data. Because one of the things you have to ask yourself is, if you're going to split a $100 billion company into 2 still sizable companies, and we're still talking about $55 billion companies, so there's going to be 2 HPs, one focused on enterprise and one focused on consumer. How do you go about splitting a 75-year-old company, which has got 300,000 employees, which has 750 sites across 170 companies? It's a large task. Obviously, splitting the employee base is quite easy. We know who works on the enterprise side, we know who works on the PC side or the printing side. We can look at HR, fairly simple to separate, because HR supports the businesses. Finance, not so bad, being able to change from one side to the other. Legal, a bit more tricky, because we have one legal department, but we can split it. But then we come to our IT department. So our IT department has grown and has evolved as the company's grown and evolved. And so for us, IT is a very important part. So if you think about what we have to do now in terms of splitting our company aside, during the next year while we're doing this, IT is still going to do innovation for us. Still got to accelerate our services. It's still going to keep our company running. It's still going to work within budget, and it's still going to manage risk in terms of everything we do. But it's got to do that while we're actually going through a quite significant change in the company. And one of the reasons that we're able to do this and be able to look at that particular problem in a particular way is that in the past we've made very big investments in cloud, specifically mobility, security, and big data. So we understand the 4 key tenets which are driving a lot of change in the industry. Just a quick flash chart about our IT department. It's a very big IT department. Like I say, we're a Fortune 10 company, global base. We have about 45,000 servers sitting there in 6 data centers around the world. We have 85 data centers. Over the last few years, we've consolidated down to 6 data centers. Luckily, most of those servers are virtualized, so we run our own internal clouds, pretty much. We use a combination of VMware, Microsoft, System Center, any VM layer, you name it, but we have everything virtualized. But we still got something like 100,000 routers spread across the company. So our network presence is huge. We have about 63 petabytes of storage that we use to run the company, of which 4 petabytes of that is replicated daily. So we have a constant chain of big data. I'm just looking at some of the facts here. We have about 300 million hits per day on HP.com that we've got to split. So we're still going to manage that traffic. We're still going to manage the common S that comes across those sites. We have about 2.5 billion security incidents that hit HP every day. I'm surprised at that, every day. That's basically denial of service attacks, all the general stuff that malicious people want to do when they try to attack our external boundaries. So we have a very large IT department with some very large challenges. So if we look at how we're going to split the company, and at the same time still do all our enterprise imperatives like doing innovations, doing the services, looking after our big data, keeping our clouds running. It's a very big task. But luckily, that's what we do. We build products and services to actually do that. So what I wanted to do today was actually just talk about some of the work that we're doing in the labs to try to support this. Because fundamentally, we're an IT company that uses IT to run our business. So any of the work that we do in the labs should be able to support this type of things before we actually get them out onto the street for other people to use. So whether it's looking at the security side, whether it's looking at our infrastructure side, whether it's looking at our software side or our big data side, everything that we do in the labs, we apply to our IT department. So the labs moving forward has a pretty large role to play in terms of how we're going to move our IT department forward to split that particular company. And by the way, one of the reasons why we talk about the new style of IT is we're not the only company at the moment who's in this particular mode. Symantec is currently going through a split. EMC is going through a split. So a lot of the large IT companies are going through splits. A lot of the service provider companies are going through change as we move more to a mobile world. So for us, just talking about the commerce side and the way that we can talk hypothetically about clouds and we can talk about what's happening in the cloud and new technologies, but when the rubber hits the road, it's companies like ours that should actually use the cloud. So that's why we call it the new style of IT, because whether you look at cloud security, big mobility or big data, those are the trends that are in hidden HP and they're hitting other companies. And those are the trends that are basically CIOs have to deal with when they're actually doing their day jobs, which is basically managing risk, providing flexible service for the organization, basically keeping the lights on across the desktop and the data centers. Some interesting facts and numbers again. This is the chart we pulled up. I think this was something we did some work with Gartner. It's amazing how quickly we actually changed the terminology. Not so long ago, most of our conversations were around kind of like the gigabyte, terabyte range. Now, most of the time when we talk about data, we're talking about petabyte getting to the exabyte. So we're actually very quickly moving up that stack. And I don't know about some of these new words like the yottabyte or the frontobyte, etc. I think these are industry standard terms. But we're very quickly going up that stack in terms of the size of the data. Before, doing data analytics over a terabyte used to frighten us. Thinking about a petabyte used to frighten us. Like I say, we have 2.64 petabytes of data that we do data analytics on. 4 petabytes of that we change daily. So very quickly we're getting up to that range. If we look at the application side, by applications we typically mean the pieces of logic that use this data on the left. And you can see the numbers are raising exponentially. The complexity is both on the data side, on the application side, which is sitting on top of our infrastructure. It's very quickly getting out of hand. So these are some of the challenges that companies like HP face with daily. So again, one of the reasons why we're doing this, there's a lot of questions that our CIOs, our lines of business are asking. What can we do with the magnitude of this data? Most of us know today we're trying to do things like real-time insights out of the data. But if you're talking about 64 petabytes worth of data, how do you actually move that data around to where you can actually make those decisions? How do you access that data? How do you secure that data? How do you integrate that data? Specifically, if you think about the fact that we're moving a lot of that data to the cloud now, you think about the bandwidth needs in terms of a cloud to be moving petabytes of information around to the places where they're going to be stored. So I think it's great these days that we're seeing a lot of cloud services which are doing things like infrastructure services or storage services. But when we start to layer things like on top like big data or mobility, there's still a lot of fundamental challenges we need to do that infrastructure layer in the cloud to enable a movement of data so you can actually do real-time analytics for companies. So again, I think the value of the data, the value we'll get on, will depend on how we actually solve some of these challenges. So there's 3 projects I'm going to talk about specifically from the lab. One's a short-term project. But when I say short-term, it's something that's hitting our production lines at the moment, which is Moonshot. Second thing I'm going to talk about is a new longer-term project that we have called The Machine, which is quite interesting for us because it's a fundamental shift in some of our thinking. And the third one's a software project called Bamboo. We'll see if we've got time to do all 3 in this particular presentation. So Moonshot for us, we started a couple of years ago, and again the question we were starting to ask was, for many organisations, servers or data centres or the cloud is actually becoming fairly central to the way that they operate. In these particular businesses, whether it's airlines or manufacturers or healthcare, IT is not just a side thing anymore, which sits there to keep things like payrolls running and desktops running. IT is actually central to the business. And so if you think about airlines going social in terms of providing personalized customer experiences in terms of how you book your travel, your hotels, etc., etc., that's predicated on cloud, it's predicated on data, it's generally predicated on mobility because most people are running around mobile these days doing these things. Things to think about manufacturing these days, everything's personalized. You don't typically go to a shop these days and buy a standalone thing. You can choose your colors, you can choose your options, etc., etc. Sometimes you can choose your logos, your names, etc., etc. A lot of stuff is then done real time. So again, IT is central to that. Healthcare. These days, again, proactive healthcare. Things that come off the devices to provide healthcare monitoring, whether it's heartbeat monitoring, blood pressure monitoring, and then getting diagnostics around that or patient healthcare around that. IT is central to those things. Which is great because I think what we're seeing is that technology is really helping to change people's lives. I mean, us as consumers or people in the hospital, not so much consumers in the hospital, but us as end users of this stuff are really benefiting from the use of technology. But in terms, on the flip side, for the people that are using this technology, it comes with a real challenge. If you think about the number of servers, 5 million servers, the servers at the moment, just in terms of the power consumption, we're using the same power of about 5 million US homes worth of servers at the moment. That's a huge energy drain on those servers which are sitting there in the data center. We're looking at about another $15 billion worth of data center costs in the coming years to actually support those servers. So we've got large infrastructure sprawl. Still, it's very complex to manage all of that stuff. Most of the IT budget these days goes to actually just keeping that stuff up and running rather than innovating. And that's only going to get worse by 2020. Some of the figures we get from the analysts in terms of the number of devices, the trillions of gigabytes of data, the millions of applications for the people are just phenomenal. So I think where we are today in terms of moving from data centers to the cloud, it's the kind of like orders of magnitude about where we're going to need to be in 2020. So for us, looking at these type of things in terms of the business that we're in, which is infrastructure, there needs to be some fundamental changes. And I think the challenge is at the moment, if you think about what actually goes into the heart of a cloud, which is a server, there hasn't really been any fundamental change in the last 10, 15, maybe 20 years. About 15 years ago, when I was running managed services, as mentioned at AT&T and Equitas, etc., you could walk into a data center and you would see a server probably about 10 years high sitting in the rack. About a year later, those servers started to shrink a little bit, probably going down to 5 years. Those servers, in a year's time, they went down to pizza box size. And probably about a year or so later, when we're talking about 2001, 2002, everything went into a blade. So the chassis changed, the chassis got bigger again, but everything got bladed. What happened was everything got denser. So you got more stuff in a rack, blades, network blades, security blades, server blades, storage blades. Everybody went blade crazy. Cisco, IBM, EMC, HP, we all went blade crazy. And then we pretty much stopped. For the last 10 years, there hasn't really been any change in terms of the way that servers are built. You walk into any data center these days, and the technology is it's a rack with a chassis and blades, whether it's a network blade, a storage blade, or a server blade. And we've really stuck at that particular point. There hasn't been any thinking about how do we actually get past that point. Because if you're stuck at the blade level, there's only a certain amount of stuff you can stuff in a data center. And you really need to figure out ways that you can get more dense. And so we've been thinking about this, and so what we come up with in terms of Moonshot is what we call it's a software-defined server. It's changing some of the ways that we think about servers. So particularly what we're looking at the moment with Moonshot is basically we call it system on a chip. It's basically everything that was on that blade we've shrunk down onto a chip size. We then take those chips and we make specific cartridges which are targeted at specific workloads. Whether that workload is to run a web server, or whether that workload is to do a Hadoop job, or whether that workload is to do video specialized cartridges. So what we're doing now is actually, rather than building general purpose GPUs for the servers, which is one size fits all, we now took the systems on chips and we actually make very specific targeted cartridges for specific workloads or jobs. We put those in very flexible fabrics, and the fabrics that we've done, we've actually redesigned the whole chassis, the racks in which these Moonshot servers sit in. Very high. Just switch that on. Can you hear me? Yeah. Okay, let's put that away. That's the way we need it. We've actually changed the chassis so that we have very high throughput on those chassis using a lot of optics. So now we can actually take the data on specific chips and we can move those things around very flexibly. And we're a very dense form factor. What we can do inside a rack now with the we can put about 45 cartridges in about for you. We can put 10 cartridges in a rack. We can get 1,800 servers in one particular rack. So think about the densities we can now get in a data center. Well, the nice thing about this, well, because of the system on the chip technology we're doing, we don't get an exponential rise of energy consumption. So some of the things we're seeing now, just in terms of, and Moonshot's only the first step on the journey that we're doing in terms of redesigning the data center for the explosion in cloud and big data is, we're using about 89% less energy for a comparable size system, which is a huge energy saving. I mean, if you think about the three things on here around space, energy, and operations costs, those are the three largest costs in the P&L for a service provider for a cloud. You know, the people to operate, the power to keep the thing running, and the space to put all the technology. And the technology itself is actually quite cheap when you look at the other three components over the lifetime of the cloud service. So 89% less energy. That means two things. One, it's more cost effective to run clouds. Two, you can actually get more data set, you can actually get more infrastructure in for the same amount of power. But the third thing, we're actually doing a better thing for the planet because we're not consuming all the electricity. So there's 5 million US homes to power the servers at the moment. That number comes down. We take 80% less space for that power consumption because we're actually shrinking everything down to a very small form factor. We've gone to cartridges instead of blades by doing the systems on the chip level stuff. Probably not such a good thing for HP, but these things are like 77% less costly. So it's actually cheaper now for a service provider to use Moonshot than to use traditional things. Obviously, we need to sell more now to make up our volume, but it's actually cheaper now, even though it costs a lot of electricity, you can save more space. But more importantly, it's less complex. It doesn't take an army of people to keep these things running. So the technology which is coming out of the labs into the production line at the moment, we think is going to have a radical shift in terms of how we actually build near-term clouds. So we're just talking about near-term clouds at the moment. Whether those clouds are for storage or for infrastructure services, it doesn't really matter. Again, some of the, we've been looking at different workloads, and we've been tailoring the specific cartridges for Moonshot for different things, whether it's real-time processing, video transcoding, doing hosted desktops, which is a very interesting use case. Very dense web hosting, etc., etc. We have cartridges to do those things. Another thing we've been doing as well is messing around with OpenStack to see what happens if we take a very dense Moonshot rack now and we run OpenStack. What does it mean in terms of the dynamics around the cloud? Because now what we're doing when we put everything in a rack, we're channeling a load of data to that rack. So what does that mean in terms of the data center footprint, the center where we put those racks? So the whole P&L discussion around the cloud using Moonshot we start to look at because it does change the dynamics of the cloud. But I think what we have is a very, very scalable, very dense footprint which can come out of HP now, out of the labs, which helps promote and drive a lot of the cloud adoption, specifically in countries like Singapore, where we're very bound in terms of space and the power that we can use to run data centers. So in terms of some of our goals to make Singapore the hub for a lot of cloud activities in the region, we think technologies like Moonshots, which are coming out of the labs, and this is one of the reasons why we do some of this research here in Singapore, are very applicable. One company that's now using Moonshot is a company called Mlock. They're a managed services provider. They provide services to hosted cloud providers. Again, they're basically about 60% space saving, reducing their energy costs by about 75%. But basically, they plan their data center for 5,000 servers. Basically, the space that they take, they can now get 30,000 servers in there. So they can actually scale their business without having to add more data center footprint. So actually, we think the Moonshot stuff is actually quite impressive in terms of what the technology we've taken out of the lab and put into our server technologies now into the production line. But for us, that's just the beginning. So that was an interesting experiment. But realistically, we didn't do anything magical. What we really did was we said, okay, look, everyone's got fixated around blades. How do we change the form factor of the blade and the chassis and the rack so we can jiggle things around a bit and we can bring the power envelope down, we can get more in, and we can basically run different things on there. It was a nice little experiment, a nice piece of technology, but fundamentally we didn't really do anything significantly different. I'm going to switch my iPad on because there's some facts and figures that need to be updated. We have a project in the lab now called The Machine, which until recently has been a fairly secretive project, but we talked about it last year in Vegas at our HP Discover, and then our CEO was talking about it. And this is really radically looking at how we change the architecture of a data center. I mean, this is basically longer term stuff. It's nothing you're going to see in the next year or so, but it's just some of the thought processes that are happening in the labs to actually really change the way that we approach infrastructure in the data centers for cloud. And so what we were contemplating is, if you look at where we're at now, we haven't changed the architecture of how we approach computer science for probably about the last 60 years. We use the von Neumann architecture. We have CPUs, we have memory, we have storage, we have a transactional system moving things backwards and forwards across those things. But nothing's really changed. We've moved from copper to optics. We've moved from servers to blades, etc., etc. But we haven't really challenged that architecture. So what we decided to do in the labs was say, well, what happens if we throw that away? And we really looked at some other way of doing things. And one of the things that predicated our thinking about this was something called the memristor, which is something that we didn't really, well, I guess it's unfair to say that we discovered the memristor in the labs, because the memristor has been hypothesized from electronic engineering in terms of, the memristor being a component for many years. What we actually did in the labs, in our nanotechnology labs, was they actually proved that this thing existed, and more importantly, they figured out how they could actually extract the memristor property, put it on a chip and replicate it and make this scalable. So they didn't invent the memristor, but what they did was they actually found out how to actually do that. It's basically an ion transfer across a particular memory substrate, and we actually put that onto a wafer. And so what we started to think about that was, well, what can we do with a memristor? It's basically it's a resistor with memory. You can do some very, very interesting things. Obviously, one of the more simple things you can do with that is looking at that to be a memory replacement. But you can also look at things, well, can we actually start to change chips now so that we can do things like pattern matching capabilities of the human brain, which is some of the experiments that we have going on. So anyway, so we had this research team looking at memristor, and they were also looking at how we can put these on wafers and how we can put those wafers into different types of chips. So we thought it would be very interesting experiments if we could actually say, okay, if we took the memristor and we took something like photonics, as an example, if we got rid of all of the copper out of the system, we took the memristor and we took photonics, could we actually change the way that we build computers? For example, could we build special purpose cores, which are not based on von Neumann architectures anymore, based on something else, which I won't talk about because it's some of the stuff still in the labs. And could we also use memristor to build I'm talking about massive memory pools, and we bring those things together in optics to actually change the way that we actually do calculations. It's not your traditional RISC chipset type calculations. So that's what we started playing with. We've got memristors, we can build these things into chips, we can build processing chips and memristors, we can build memory chips with memristors. We've got our nanotechnology labs which are looking at photonics, what can we do? The interesting thing about photonics is it destroys distance, which is one of the nice properties. So it's a lot cheaper and a lot easier to move light across a data center than it is to move electrons across a data center. So if you can actually get some of the challenges around the laser side, the transmission and the receiving lasers, and you can bring those things down so that you can do things like internal chip communications. So you've got optics on the chip, and then you can expand that out to do optics in a machine, and you can expand that out to do optics in a system, and you can expand that out to do optics across a data center. But at the same time, you've got to do that at scale, and you've got to do it at cost. Then you can start to actually change some of the dynamics about how you think shifting data around. And it's actually not so much the memristor, but it's the optics which is allowing us to actually change the way we think about computation. Because if you think about a blade, if you go into any of the data centers around and you look at the two components that are still on a blade, which actually binds us to the traditional way of doing things, there's a CPU on there and there's memory on there. And those things are very close together because they have electrical dependencies backwards and forwards, and it's very difficult to actually break that blade in half and put the CPU one side and the memory on the other side. You can't really do that with a traditional blade. But if you introduce optics, where you can move things at the speed of light, you can actually move those distances apart. So then you can start to think about, well, what can I do now? I can build pools of CPUs, and I can build pools of memories. So the instruction sets can be over here. And by the way, if the instruction set's over here, then why have I got a piece of CPU which is bound to that instruction set? Now I can actually rethink virtualization. Virtualization is a software trick at the moment that allows you to do parallelism on a set of hardware resources. But the only reason why you do that is because of the binding between instruction sets and CPUs, so you need to be able to take things off and bring things on. But if you separate those things now, you can use the same piece of CPU for any instruction set. So you can have a massive pool of memory here with CPU which can work across these things without software layers of virtualization. and we can do that because of optics. So bringing optics together and bringing memories together was some important experiments we started to do. Another thing we decided to do was to flatten what we call the volatility stack. If you think about servers today, probably about 90% of the work that happens inside a server is actually shuffling data between the various layers, between on-chip caches, main memory, mass storage, and sometimes you've got 10, 11 layers in there. And you have to do that because of the architecture. And so most of the time today, when we're writing operating systems or writing programs, etc., a lot of the work is actually figuring out how do we move stuff around, how do we communicate, how do we break things down, mainly because of that trade-off between memory and core. So again, what we've decided to do, what we're experimenting now with a Memristor is flattening that into a single hierarchy and using optics, using special cores to actually work across that universal memory plane. So the way that we think about things when we talk about the machines in three layers, compute, communicate, and store. And realistically what we're doing is we're going to use electrons to compute, we're using photons to communicate, and we're using ions to store, which is the Memristor side. So basically this experiment we're doing at the moment, and we don't have everything worked out, this is a longer term project inside the lab at the moment, but we're actually building various systems and putting these systems together to experiment to see what we can do. But again, we're actually moving past the electron stage, which is currently where we're at in the data centers. We're taking photonics as a given. We will solve the photonics problems, either on a chip, between a chip, or across the data centers. And now we're bringing chemistry into the mix, as we're going to start using ions to provide our storage layer. That will significantly change things like the densities that we can do inside a particular chip, inside the system. It significantly changes the power envelopes of the data centers. And I've got a slide later on which talked about some of that stuff. It really changes the dynamics about how you can actually build a data center. And we're going to need to do that. And as I mentioned, it's interesting coming 4 years later to look at how the cloud has been adopted, not just in Singapore, but I spent a lot of time in the Valley, Silicon Valley, just around the world. But if we go the next 4 years, and the next 8 years, and the next 10 years, and we stick more and more stuff on the cloud, whether it's petabytes of data or more VMs, we're going to fundamentally have to change what goes into those data centers, specifically on islands like Singapore. Another thing we're doing, obviously, what we have to do, if we're going to fundamentally change the hardware there, we need to build a new operating system, and that's something we're doing on the system side. It's interesting for us because we haven't really, from the labs, contemplated a new operating system for many, many years. We built HPUX, various flavors of Linux, but again, we're having to think about a new operating system for the machine. One of the important things we're doing is we're looking at security from the silicon upwards. And again, we're not taking security as an afterthought. Security is one of the banes of our life at the moment. As we move out into the cloud, as we have more and more data out there, security is just a big headache. And even me, I came to Singapore, I got a phone call from my bank a couple of days ago. One of the shops I go to in California was a hardware shop had been hacked into. It's Home Depot. Like millions of credit cards have been stolen. They had to cancel my credit card, blah, 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 blah. So it's just like it's a bane of our existence. Everything we do today, we seem to get a security hack. So again, security in terms of the machine is the first class citizen. Again, we're also looking at how do you do things like a million node management. If you're putting everything really, really dense, you need to be able to manage that stuff. So we have technologies called something called Loom, which we have in the lab at the moment. Loom is a data visualization technology for VMs, which we're currently rolling out as part of our Helium cloud stack. Allows you to do things like very easily manage 40,000, 50,000, 60,000 VMs on a single pane. There's some very large scalability things we need to look at in terms of the operating system there. Right up to how do you do analytics across a huge memory pool. So some very interesting work that's happening in the lab. Just some performance estimates that we were doing. We were doing some experiments and some emulations. We were comparing against things like the BlueGene system of Livermore, which is a million cores on 64,000 nodes. We were doing some comparables in terms of things like graph searches. The interesting thing for me on this graph was not so much around performance or problem size, because you can state the problem differently. It was just on the power that it took to actually do something like, what was this? This was a Graph 500-like workload. And it was just chalk and cheese in terms of what it takes on the traditional server farm to do that graph search. For this particular thing, it was about 8 kilowatts. So what we were doing on the machine, which was like half a kilowatt, it was just chalk and cheese. So if you think about that in terms of scaling out data queries across the web, the standard thing at the moment is if you do a Google search, you do 2 Google searches, you boil in a kettle of water. pretty much what they say these days because of the amount of electricity you're using. It's a significant effect. So watch that one because this is a very interesting one for us. This is a long-term research goal that we're doing to complement our moonshots. Probably another couple of years. And we probably won't come out with a thing called the machine. There won't be a server called the machine. But what we'll start to do is roll out some of these technologies in some of our servers to actually, as we migrate away from moonshot, you'll start to see more of the Memristor, the photonic stuff coming into our servers. So the last thing I want to talk about is something completely different. It's more on the software side. Is a project we have called Bamboo. And again, what we were looking at here is cloud and big data. Two common themes for us at the moment in the research lab. Two common themes across HP, and I think it's two common themes across the industry. Because no matter where you go these days, everyone's talking about big data. And I hate the big data term. I think for me it's just data. We actually have some dimensions we have to work across, and things like velocity, volume, and variety. But it's just data. But the overlap between cloud and data and how you do analytics and searching across this data is huge. So interesting. Oh, my icon did disappear. Never mind. See, it's a Dell machine, not a HP machine. I can see it differently on here than what I see on the screen, but never mind. What we're looking at here is the relationship between domain experts, data scientists, and software developers. So if you want to build any complex data analytics system at the moment, traditionally you need those three people. You need someone who knows about a particular domain, whether it's gene sequencing, etc., etc. People who understand the algorithms to do search across those things, clustering, classifications, etc., etc. And you need engineers that can actually put those things together and build those types of systems. You look inside a country like Singapore and in Silicon Valley these days, finding a data scientist is like trying to get blood out of a stone. Finding a pool of data scientists that we can attract to come into HP or to come into any other company to work with our software engineers and our domain experts to build things is very, very tricky. Everyone at the moment is scrambling for data scientists. The top three skill sets that are in demand at the moment, just in case anyone out here is doing computer science and wants to get out there into industry, it's UX people, mobility people, and data scientists. In Silicon Valley, if you're a good data scientist, you can practically write your own ticket in terms of salary that you wanted. I just lost one of my engineers to Google in the Valley. So what we were looking at here was to say, look, okay, cloud and data analytics go together very well. How can we use the cloud as an ecosystem, but particularly what can we do to bring together domain experts, data scientists, and software engineers together so that if anyone's got a particular big data problem that they want to do, we can actually come to a particular, there it is. There we go. We can actually get these people together to actually build a particular system. So we thought about this thing called Bamboo, which is something we're building. Actually, we're building this in the Singapore lab. So this is something specifically in the Singapore lab. It's basically an ecosystem platform which allows us to bring together data scientists, domain experts in a particular field. It doesn't really matter what field. It could be smart city, it could be oil exploration, etc., and software engineers. So that we don't have to own everything. So, for example, if I should be able to come to Bamboo and say, I've got a very interesting problem around. I work for Shell. I've got a very interesting problem around oil exploration. Can I come into here, find some data scientists, which maybe sit in Venezuela because there's large oil fields in Venezuela, get some oil domain experts and get some software engineers and bring them together to actually build an application for me to do, I don't know, maybe substrate analysis on the Gulf of Mexico to look for particular oil packets. Those type of things. Because I don't want to actually attract all of these software engineers, all of these data scientists together to work with inside my organization. So we built Bamboo specifically for that, so that any organization can have access across the globe or across a particular region to data scientists who can work together. We're launching this in Singapore, and probably my financial year begins at the end of October, but probably in the new calendar year. I hate these little slides. So Bamboo is predicated on three layers: data, analytics, and visualization. A couple of things we're doing in the cloud here. We're actually building a very large query engine sitting on top of a distributed file system. It's Hadoop, sitting on top of a Hadoop system, with an analytics, proprietary analytics workflow library system that we're building at the moment. On top of that, we're seeing a bit of visualization there. So we haven't launched yet. We haven't figured out how we're actually going to do this or make it available to the general public. But you'll be able to do something like come to www.bamboo.com, register, log in, express a problem. Some data scientists will say, okay, I've got some ideas about how I can solve your problem. You can bring in some software engineers, and collectively, collaboratively, you can actually sit down and figure out the data that's needed for that particular problem, where the data will come from, components from the analytics library to bring together. If that analytics capability is not there, and if a data scientist can express it, you can bring in a software engineer to actually code up that particular thing and put it in the library, and use the visualization techniques or the visualization libraries from Bamboo to actually do the visualization of your particular problem. So again, just at the data layer, again, this is why the cloud is very important for us, because we need to bring in mega globs of data. One thing we can do with Bamboo is actually connect remotely to data, or you can bring your data into a Hadoop file system. And what we were trying to do here was make it very easy for people to do. Let me build slides. We make it very easy for people to approach data analytics. What we want to be able to do is for people to express their problem without having to worry about how you actually get applications built or where you find people. We want people to be able to come and say, I want to do X. So we try to make it as simple as possible, just in terms of connecting to databases, sucking data up. The connectors that we provide in Bamboo, you can bring anything from Teradata down to a MySQL database. You can either import it or use it remotely. Just in terms of how we analyze the data, what we did is we built up an analytics workflow engine. It's basically a way that you can actually break down your analytics task into subtasks and look for particular things like sentiment analysis or clustering or classification techniques to manipulate the data as you go along. So you can express your, as a domain expert, you can express your problem as a workflow rather than a system. And you can work together with software engineers and data scientists to actually build that workflow on the fly. And give an example of the workflow. And again, what we will then do, we have a parallel data analytics engine which is built on top of Hadoop. It's a fairly large Hadoop cluster that we have running with one of our service providers, so that we can do multi-tenancy job execution. And you can run those jobs once, one-off, on a daily basis, a weekly basis. And then, again, what we can do then is find ways that we can do visualization. So people can come in with various visualization techniques. I don't like the way that looks. Again, data scientists will say, well, if you actually move from a pie chart to some of these bubble representations, it would look better. Bring in a software engineer to build a bubble representation. Maybe someone else can use that later on. So what we're trying to do with Bamboo is make data analytics easy to use. It's kind of like different from what we do in some of our other labs, which is looking at the thorny problem, how you actually build servers. We were looking at how, if you have data analytics in the cloud or storage in the cloud or CPUs in the cloud, how do we make it easy as possible? How do we get away from people having to program as an end user or as an next level user? How can we do one-click type building of data analytics applications? So that's it. That's what I wanted to talk to you about. Realistically, I want to give you some indication of how companies like ourselves are embracing changes in IT. And specifically, I was using the use case of HP because we're going through a massive transformation at the moment. And the fact that we've been making investments in cloud and big data, and because we're so mobile these days, to talk about that. Just talk about the fact that some of the lab technology we're building, we're actually applying to the HP business. Moonshot is an exciting technology for us because it solves some of the problems that we have in the data centers in Singapore. But longer term, doesn't really matter whether it's HP, IBM, or Dell. If we want to keep up with the scale of advancement of the cloud in terms of how many CPUs are going into the cloud and how much data is going in the cloud, there's some fundamental problems that need to be solved by the industry. And scale and complexity and power consumption and density, those are some of the challenges. And more specifically, I think one of the interesting use cases in the cloud at the moment is around big data. Because no matter where you go these days, and in Hong Kong the other day, with the government in Hong Kong, everyone's talking about big data. So I'll stop there because I had my 3